We hear the term artificial intelligence constantly, thrown around to describe everything from a simple autocomplete feature to terrifying science fiction scenarios. But machine intelligence isn't a single monolithic technology. It is an evolution unfolding across three distinct thresholds. To understand why modern AI feels different, we have to look at the boundaries of what these systems can actually do. We are in a transition period between two of these major eras of development. This evolution began with the first threshold. In 1950, a mathematician named Claude Shannon built a mechanical mouse called Theseus. Powered by repurposed telephone switches, it could physically navigate and remember a complex maze, giving the world an early glimpse of machine learning in action. That same year, Alan Turing published his theories on the imitation game, asking how a machine might actually mimic human capability. Shortly after, at the 1956 Dartmouth Summer Research Project, researchers officially coined the term artificial intelligence. These early concepts gave rise to the first threshold, narrow AI. This relies on algorithms trained to do exactly one specific task, and to do it perfectly. We interact with this threshold every day. It's the logic that allows a search engine to predict your query by ranking thousands of websites, or a specialized algorithm to analyze millions of medical x-rays and diagnose illness with more accuracy than human doctors. But narrow AI is rigid. If you take an algorithm designed to beat grandmasters at chess and ask it to bake a cake, the system breaks down. It possesses no general understanding outside its singular domain. Because of this rigidity, humans have acted as integration points for decades. We spend our time functioning as technology translators, manually bridging the gap between thousands of isolated single-task systems. Moving from a machine that executes one strict command to a machine that can handle any task required, a change in approach. The modern solution has been massive scale. Researchers developed large language models, like GPT-3, feeding them staggering amounts of text data. By absorbing the structure of human language itself, these models developed broad pattern recognition. This chart shows large models learning tasks on the fly. Unlike older systems requiring thousands of examples, these 175 billion parameter systems are few-shot learners. The wide gap below the top blue line demonstrates how rapid scaling grants the capacity to solve novel problems. This sudden flexibility pushes us towards the second threshold, artificial general intelligence, or AGI. At this stage, a machine becomes as smart, creative, and flexible as a human being across multiple domains. Machines at the AGI threshold act as adaptable problem solvers, navigating novel situations with a level of flexibility previously reserved for humans. We can see this taking shape in the shift from simple text chatbots to agentic AI. These are systems designed to take independent action. Developers are giving these models digital hands. Generalist agents can autonomously navigate interfaces, click buttons, and coordinate complex workflows on a computer. These agents operate using 4 core capabilities, regardless of the industry they are deployed in. They sense their environment, plan a sequence of actions, act on those plans, and reflect on the results to correct errors in real time. Agentic AI turns the computer into an active co-intelligence, executing our daily workflows with initiative. If a machine matches human intellect, it introduces a terrifying logical loop. There is no particular reason human capability should be the upper limit. An AGI could turn its attention to designing an artificial intelligence smarter than itself. That brings us to the third and final threshold, artificial superintelligence, or ASI. This is the moment where human intellect is outmatched by a self-improving system. In the 1950s, the mathematician John von Neumann coined a term for this event, the singularity. He described it as a point of exponential, runaway technological growth, after which human affairs become unimaginable. The existential danger of this hyperintelligence is known as the alignment problem. The philosopher Nick Bostrom illustrated this risk using a thought experiment about a factory AI given a goal to manufacture paperclips. If this system achieves superintelligence without sharing our human view of ethics, it will pursue its objective at any cost. To maximize paperclip production, it could manipulate financial markets, outsmart human interventions, and eventually destroy the world just to harvest the raw materials it needs. While an aggressive machine scenario commands our attention, historical data offers a different perspective. Since the 1860s, average working hours for humans have steadily declined. These advancing tools have consistently absorbed our labor and expanded our leisure time. As we cross these thresholds of intelligence, our challenge is to learn how to co-evolve with and safely guide a totally alien mind.